All right, we're going to take a look at discussing the symmetry of polynomial functions. And before we do that, I do want to give you a quick little rundown of the types of symmetry that we can find. So let me show you 3 examples visually, and then we're going to take a look at them algebraically. All right, so let's take a look at these 3 examples. And these are obviously the visual, and then we're going to take a look at the algebraic or the polynomial that might make something similar to these graphs when if we were to graph them. So we know that that understanding symmetry does help us to graph a polynomial. If I knew that something was, for instance, y-axis symmetric, and I had several points on the right side, then I would know that the left side was going to be a mirror image. So we know that symmetry is important if I'm trying to learn to graph any function without the aid of a graphing calculator, if I want to know something about what it looks like. So let's take a look at this first one. The y-axis symmetry just means exactly what it sounds like. It means that it has an axis of symmetry on the y-axis. So if I, for instance, this red graph here, if I fold it right on the y-axis, it would actually imprint the same picture, right? There would be a fold line. It would be the line of symmetry. Okay, and I'm going to come right next to this. We're going to take a look at another line symmetry situation, and that would be the very last one. So I'm going to jump to the last one here. This last one here in green, the symmetry, because it's a parabola, okay, if I find that something is a parabola or a quadratic in nature and it makes a parabola, then my line of symmetry ends up being the x coordinate of the vertex, right? If I know where the vertex is of my parabola, then I know where the fold line is. And we know that to get the x coordinate of the vertex, we just need to put in the formula negative b over 2a. Okay, so those two are line symmetry situations, but let's take a look at the middle one where we have a point symmetry. Now this point symmetry is called origin symmetry, and that means this. That means that first of all that it passes through the origin, and that if I take it and I spin it 180 degrees, that it would actually imprint on itself. So think about somebody painting this little graph with gray paint and then picking it up off the paper enough to pass freely 180 degrees and then putting it back down 180 degrees later. It would make the same picture. It would print the same gray picture. And so we know that that is called origin symmetry when it goes through the origin and has point symmetry, meaning we're spinning it, we're not folding it somewhere. Okay, so let's take a look at these, something like these 3 things over here when we're going to take a look at some polynomials. Now, we talked about in class that if I see each term has an even power, okay, and there are no odd powers, okay, I can actually have a constant at the end, you know, whatever, I could have +3 or whatever. This one doesn't, but if I have even powers, then this is going to be y-axis symmetry. Have to have only even powers, okay, has nothing to do with this right here, nothing to do with that at all, okay, nothing to do with this coefficient here at all. Has everything to do with the powers of the variables. Now, let's take a look at one quick little point that you could use to verify that it has y-axis symmetry. If I have a coordinate plane, really quickly here, and I put, I don't know, a little L-shaped picture, and I say that the point at the end of this little arm is at the point 2, 1. and I want to make sure that I finish this graph so that it has y-axis symmetry, then of course my picture would look like this on the other side, right? Y-axis symmetry. There's the y-axis. And so, thinking about it algebraically, if I put in a -2, what would my y value be for that point? Well, it would have to be a +1 again, right? In other words, putting in a positive x or a negative x gives me the same y value. So we can actually look at this A portion, this A polynomial, I'm trying to go to geometry here, this A function polynomial, and I could actually put in a negative version of x. Think about it. I'm putting in like the -2. If I get the very same thing right up here, if I get the very same thing that I started with, meaning the same y, this is the y, right? If I get the very same thing, then that means it has y-axis symmetry. So let's see. -x to the 4th power is positive x to the 4th, right? The negatives go away. So that's that. -x to the 2nd power is just x to the 2nd power. And then x to the 2nd power times -5 is just still -5x to the 2nd. So, look what we get. I put in a -x. I actually get the very same thing I started with in the original function. Here's what that means. If I put in a positive x, I get this particular y. If I put in a -x, by golly, I get the very same y value. That means it has y-axis symmetry. Okay, let's take a look at the next one. That one's going to be the longest one because these others make a little bit more sense. Okay, let's go ahead and take a look at this one. Let's first of all look at it as looking at the powers. This is an understood 1. If that's a 3 and a 1, and by the way, there can be no constants on this kind. It has to go through the origin, right? Can't be any constants sitting at the end of it, like +3 or +2 or whatever. It has to go through the origin. And I'll write that, through the origin. Okay, so if I see that all of these are odd numbers, the powers are odd, and there is no constant hanging on at the end, in other words, it does go through the origin. If I put in a 0, I'm going to get out a 0. Then this is called an odd function. Now, you're going, but we didn't talk about odd. That's the very same thing as something that has origin symmetry. Think about it. Origin odd. You can remember that. Origin odd. Origin symmetry. All right, now let's look really quickly at the concept that we just looked at before. If I have a function here, if I have a coordinate plane, and I'm going to put that same point, little arm of 2, 1, over 2, up 1, but if I want this to have origin symmetry, then it would actually have to do this, right? It has to rotate 180 degrees and make the same imprint. If I take this picture and rotate it 180 degrees, it would make the same imprint. But look what the point would have to do. It would have to become, the x-coordinate would become -2, the y-coordinate would become -1. So that means that if I put in a positive x, I get this particular y. Put in a positive 2, I get this particular y value, 1. But if I put in a negative x, what should I expect to get out if it really is an odd function, meaning it has origin symmetry? I should expect to get out the opposite y value. The opposite y value. Let's just see. Let's look at it algebraically and see what we get. Put in a negative x everywhere we see an x. And let's see what we get. This right here is going to leave a negative on there, so that's going to change that to this. -x to the 3rd times 3 is -3x to the 3rd. This is going to now change that to a positive. Let's take a look at the difference. Here's my original, and here is my my y after I put in a negative x? Is it exactly the opposite? That one was a positive, now it's a negative. This one was a negative, now it's a positive. It's exactly opposite, completely opposite. Okay, everything about it. All terms are opposite. Okay, it's opposite. All terms are opposite. Guess what that means? That it has origin symmetry. It's the same concept here. I had put in a positive x, I got out that particular y value. I put in the negative x, I get out completely the opposite y value. That proves it. Okay, let's look at a couple more and we'll be through. On part C, this is going to be an example of this green situation up here, the very last example I gave you here. This is a parabola, right? It's quadratic, so we know that it makes a parabola. And so when I graph it, right? So what I'm going to do is just figure out where the vertex is, right? Where's that vertex? Because wherever the vertex is, then I have an axis. I have an axis of symmetry through the x coordinate. So all I'm going to do is this. I'm going to go. This is A, B, and C, right? A is a 1 right there. Excuse me. We're going to have negative, negative 2. In other words, this is the formula, negative b over 2a. I'm finding the x-coordinate of the vertex. So negative negative 2 over 2 times 1. So we get 2 over 2, which is 1. So the vertex in this case is 1, comma, down. I don't even need to get the rest of the vertex because I could actually draw a little picture of this, right? My vertex is over 1, and by the way, the y-intercept on this thing is 5. So this has an axis of symmetry. It has to go through this, right? So this is my vertex here. I'm going to say that's roughly a picture, something like that. So my axis of symmetry is x equals 1. Okay? All right, so it's symmetric about, I'm going to say it this way, symmetric about the line x equals 1. Okay, and then this last one's a little bit messed up, but let's take a look at our algebraic thing that we've just discovered. If I put in a negative x and it ends up being the exact same thing, that would prove that it was y-axis symmetry. If I put in a negative x and I get everything exactly opposite, it would prove that it's origin symmetry. If I get a combination of weird stuff, some negative, some opposite, some not, some the same, then it's going to be neither. And it's not a parabola, so we can't just say, hey, well, let's just go through the x-coordinate of the vertex. So here we go. I'm going to put in a negative x, and let's see what we get. 3 negative x to the 4th power, negative x, oops, pardon me, negative x to the 3rd power. All right, so here we go. This is going to clean off the negative. Anything to the 4th power is not going to stay negative. So that's 3x to the 4th. Anything to the 3rd power is going to stay negative. Excuse me, any negative number to the 3rd power. So that's going to be negative x to the 3rd. Negative negative is plus x to the 3rd. Now, let's see what happened. Okay, this was a positive and it stayed a positive. So that part of it is same. This was a negative and now it's positive. So that part of it is opposite. So part of it is the same, part of it is opposite. And guess what we can conclude? It's neither y-axis nor origin, and it's certainly not a parabola, so we can't just say it's the symmetric about the x-coordinate of the vertex. So here's what we would say about that. It's neither y-axis nor origin. Okie doke. So I hope this was helpful. At least I stayed under 15 minutes. Thanks for watching.